Welcome to the deep dive. In a world that's just absolutely overflowing with information, where every click promises enlightenment but often just delivers more noise, how do you actually get truly well informed?
Yeah, without feeling like you're just drowning in data. I get.
Exactly. That's where we come in. We take that stack of sources, articles, research, maybe even your own notes, and we just distill it. We pull out the most important nuggets, those surprising facts, maybe a bit of humor.
Just enough to keep you hooked.
Think of us as your personal shortcut, helping you get well-versed and ready to tackle whatever comes next.
Indeed. Our mission here is really to guide you, help you cut through all that density and really understand what's most critical in the material you've shared with us. It's about getting those aha moments, not just, a flood of information.
Couldn't agree more. And today, we are diving deep into a topic that's just foundational to so much of what we see in AI and data science: classification functions within scikit-learn.
Scikit-learn.
Yeah. Now, if you're working with the data, or honestly even just curious about how machines learn to make decisions, scikit-learn is the powerhouse Python library for machine learning. It's like the backbone for countless applications out there.
Oh, absolutely. It truly makes these complex machine learning tasks remarkably accessible. I mean, whether you're trying to analyze customer behavior, maybe predict who's likely to churn from a service.
Or predicting medical outcomes, right? Critical stuff.
Exactly. Or even enabling your smartphone to recognize a handwritten digit you've just, scribbled on the screen. Classification is really at the core of all these sophisticated operations. So this deep dive will unpack how scikit-learn makes these tasks, which seem really complex on the surface, so approachable. We'll peel back the layers, reveal the underlying mechanics, and really highlight the key things you need to consider to build robust and effective models.
That sounds like a fantastic roadmap. I'm really eager to get into the specifics. So what's the journey look like for today?
Well, we're starting with the foundational APIs scikit-learn provides. Then we'll move into some specific widely used algorithms, things like ridge classifier, perceptron, and logistic regression.
Okay, the big names.
Right. But we're not stopping there. We're also going to explore more advanced topics, like how scikit-learn elegantly handles multi-class and multi-label classification problems. These pop up all the time in real-world scenarios.
Yeah, those are super common.
And then we'll move on to the absolutely critical art of evaluating model performance, because, training a model is really only half the battle.
Oh, definitely. Knowing if it actually works is key.
Exactly. And finally, we'll get into the nitty-gritty of fine-tuning those hyperparameters to squeeze the most performance out of your models. We'll even try to peek behind the curtain a bit, see how these models actually learn to make predictions, give you a glimpse into their thought process, so to speak.
Love that. A glimpse into the machine's mind. Okay, that's a fantastic overview of why classification is so fundamental. To really master it in scikit-learn, I think we first need to get a handle on its core toolkit, right? Those universal functions that underpin pretty much everything.
Absolutely. When we talk about scikit-learn's classification APIs, you can broadly think of them in two main types: generic and specific.
Okay, generic and specific. Walk us through that distinction. Why does it matter?
Sure. It's quite an elegant distinction, actually, and understanding it really helps. So on one hand, you have the generic APIs. The prime example here is the SGD classifier.
SGD, stochastic gradient descent.
Right. Stochastic gradient descent classifier. What's really interesting about SGD classifier is its flexibility. It's less like a single fixed algorithm and more of a versatile framework for linear models.
A framework, okay.
Yeah. It uses stochastic gradient descent for optimization. That's an iterative approach where it updates the model's parameters one sample at a time, or maybe in small batches. This makes it incredibly scalable.
Scalable how? Like for massive data sets?
Exactly. We're talking problems with, say, more than 100,000 training examples, maybe even 100,000 features. Huge scale. And it also works beautifully with sparse data.
Sparse data, like in text analysis, where most values are zero.
Precisely. Text classification, natural language processing areas where you have tons of potential features like words, but only a few are present in any given document. SGD classifier handles that really efficiently.
That sounds incredibly powerful. So it's not just one algorithm, but you called it a framework. What does that flexibility actually unlock for someone working with big, messy data sets?
Well, it means you're not locked into one specific algorithm, right?
Yeah.
You can, for instance, pivot from doing, say, a linear support vector machine to logistic regression just by tweaking a single parameter of the loss function.
Oh, wow. Just change the loss parameter.
Yeah. It makes it incredibly agile for prototyping and experimentation. If you're not sure which linear model is going to perform best, SGD classifier lets you try out a bunch of variants with minimal code changes.
That's handy.
And maybe more profoundly, its reliance on SGD means it scales beautifully to those massive data sets, sometimes way beyond what other classifiers can handle in memory. Plus, its robustness with sparse data is a huge win for things like text analysis.
Okay, that's super neat. So that's the generic SGD classifier. Then we have the specific APIs. How do they differ from this versatile beast?
Right. The specific APIs think logistic regression perceptron ridge classifier. They use specialized, often highly optimized solvers for their particular optimization problems.
So they're more focused.
Exactly. They aren't as broadly customizable through just that one loss parameter like SGD classifier. Instead, they come sort of pre-configured with a specific goal in mind, and their internal solvers are really tailored for that goal.
Okay.
But, and this is an important insight, many of these specific estimators are actually equivalent to an SGD classifier with a particular loss function and maybe some other parameters set.
Ah, so they're related under the hood.
Very much so. For example, an SGD classifier set up with loss, perceptron, at a 0-1 learning rate constant, and penalty. None. Well, that's effectively the same thing as using the specific perceptron instance.
I see.
So the specific ones offer convenience and sometimes slightly better performance for their specific task because their implementations are so highly optimized.
Okay, so generic gives you that raw power and flexibility, great for huge data sets or trying things out quickly. Specific ones are like pre-tuned tools for common jobs. Makes sense. Now, regardless of which type you use, there are these common methods, right? The ones that almost all scikit-learn estimators implement for training, prediction, evaluation. That consistency must be a lifesaver.
Oh, absolutely. This consistency is a core part of scikit-learn's design philosophy. These are the universal actions you'll perform across nearly all estimators, giving you that intuitive workflow. First and foremost, you have fit, XY.
The big one, training.
That's the one. This is the method for model training. You feed in your feature matrix. X, think of it as your input data. Rows are samples, columns are features.
Like pixel values or customer info.
Exactly. And then you provide Y, your labels, the outcomes you want to predict, like spam, not spam, or digit 0 through 9.
Okay.
And fit is where the model learns its parameters. It adjusts its internal weights, its biases, to best map those inputs X to the outputs Y. It's literally where the machine learning happens, finding patterns in your data.
That's the core learning step. So once it's learned, how do you actually use it? Make predictions on new stuff it hasn't seen.
Right. For prediction, there are primarily two methods you'll use. The first and most common is predict.
Predict. Straightforward.
Yep. You give it a new feature matrix, X, usually your test data or unseen samples, and it just returns the hard, definitive class labels the model predicts. So if you're classifying emails, it tells you spam or not scam. It gives you the final verdict.
Okay, the final decision.
Yeah.
But sometimes you need a bit more nuance, right? Not just yes or no.
Precisely. And that's where the second method comes in. Typically decision function X, or sometimes you'll see predict probe X for probability estimates.
Decision function. What does that give you?
So while predict gives you the label, decision function is incredibly valuable because it gives you a confidence score for each sample. For a binary classifier, this score might represent how far the point is from the decision boundary, basically, how strongly it falls on one side versus the other.
Ah, so it tells you how sure the model is.
Exactly. For multi-class, you might get a score for each possible class. Understanding this score is crucial because it gives you insight into the model's certainty. A score far from 0, or the boundary, means high confidence. A score close to the boundary means less certainty.
And that could be really useful, right? Like maybe you only act on high confidence predictions.
Absolutely. Think about medical diagnosis or maybe fraud detection. You might need a certain level of confidence before taking a critical action or triggering an alert. Decision function gives you that insight.
That's a really important distinction. Confidence matters. Okay, so we have fit to learn, predict for labels, decision function for confidence. What about checking how well it did overall?
For evaluation, the main one is the score XY method. After you've trained your model, you use score on some unseen test data where you do know the true labels.
Okay, so you need labeled test data.
Right. You provide the test feature, matrix X, and the true labels Y, and score typically returns the mean accuracy on that test, set the percentage it got right.
So it gives you a quick overall sense of performance?
Yeah, it's a convenient first check, though, as we'll discuss later, accuracy alone often isn't the full story, especially with imbalanced data.
Good point. We'll circle back to that. So fit, predict, decision function, score. That's a solid toolkit.
Mhm.
Are there any other common methods worth knowing for just like managing the model itself?
Yes. A few miscellaneous but really useful ones.
Yeah.
Getparams lets you retrieve the current parameters of your estimator, like the settings you used.
Hmm.
Super handy for inspection or debugging.
Okay.
Then separams lets you change those parameters after you've created the model, maybe for tuning. And then there are densify and sparsify. These are about converting the model's internal coefficient matrix between dense and sparse formats.
Ah, relevant for that sparse data we talked about, like text.
Exactly. If you have very high-dimensional data where most values are zero, using sparse representation saves a ton of memory and can speed up calculations. So these methods let you control that format. Collectively, these common methods provide that consistent, powerful interface across different algorithms, which is a huge part of what makes scikit-learn so user-friendly.
That's a fantastic overview of the core functionality. Really helps to see the common ground. Now let's move on to actually using some of these. Shifting gears a bit, I'm curious about the ridge classifier. The name makes me think of ridge regression. How does it make that leap from regression to classification?
That's a great observation, and you're absolutely right. The ridge classifier is indeed a classifier variant of the well-known ridge regressor. Its fundamental goal is the same: minimize a penalized residual sum of squares.
Okay, so it's still minimizing squared errors, like in regression.
Essentially, yes. But it adapts this for classification. In regression, it's finding the best line or hyperplane to minimize the distance to continuous values. For classification, it tries to fit a continuous output that then, through a simple transformation, maps to your discrete classes.
And the penalized part, that's the regularization, right? Like in ridge regression.
Exactly. The ridge part refers to L2 regularization, which helps manage model complexity and prevent overfitting by penalizing large coefficient values.
Okay, so how does that translation work for binary classification? Where you have just two classes, like yes or no.
For binary classification, Ridge Classifier cleverly treats the problem as a regression task. First, it usually converts your two target classes, say negative and positive, into numerical values, typically manic 1 and plus 1.
Okay, makes sense.
Then, it runs a standard ridge regression, trying to predict a continuous value based on those manic 1 plus 1 targets. The predicted class for any new sample then simply corresponds to the sign of the regressor's prediction.
Ah, so if the regression output is negative, it predicts class -1. If positive, class +1.
Precisely. If it predicts, say, -0.5, the class is -1. If it predicts plus +0.7, the class is +1. It's a neat way to leverage a regression technique for classification, especially if you have lots of features.
That's pretty clever. And what if you have more than two classes, like in a multi-class scenario, identifying different types of fruit, maybe?
It extends quite naturally using what's often called a one v sol or one v rest approach internally. For multi-class classification, Ridge Classifier treats it as a multi-output regression problem.
Multi-output regression.
Yeah.
Okay.
Instead of just one output, it tries to predict multiple continuous values simultaneously, one for each class. So for a given input, it will generate a score for apple, a score for banana, a score for orange, etc.
And then it just picks the highest score.
Exactly. It predicts the class that corresponds to the output with the highest value. If it predicts 0.8 for apple, 0.2 for banana, and 0.1 for orange, it classifies the sample as apple. It's basically running multiple binary-style regressions in parallel and picking the winner.
Okay, so it's about twisting the classification problem into a regression one. Interesting paradigm. How do you actually train it and control that regularization?
Training is very standard scikit-learn style. You first instantiate a Ridge Classifier object. Often you start without any arguments, just Ridge Classifier, to use the defaults.
Simple enough.
Then you just call the fit method, passing your training features, xtrain, and your labels, itrain. Remember, for binary, itrain is a vector. For multi-class, it handles the multiple outputs implicitly through that internal one-v-sol strategy.
Got it. And that penalized part, the regularization strength, how do you control that?
That's controlled by the alpha parameter. Alpha dictates the strength of the L2 regularization. You set alpha to a positive float value. Its default is 0.1.
Okay, alpha. And how does its value affect things?
Here's the crucial point, and it's consistent with ridge regression. A larger value of alpha means stronger regularization.
Larger alpha, stronger regularization. Okay.
Yeah. This helps prevent overfitting by shrinking the coefficients, making the model simpler, and hopefully generalizing better to new data. It's a trade-off, though. Too little alpha, and your model might overfit the training data. Too much alpha, and it might become too simple and underfit, failing to capture the real patterns.
Right, that classic bias variance trade-off. So bigger alpha pushes the model towards smaller, more spread out coefficients. Now, to actually solve this optimization problem, I saw Ridge Classifier has quite a few algorithms or solvers.
That's right. It offers several robust solvers: SVD, Koleski, Sparseg, LSQR, SAG, Saga, and PalmBFGs, while you generally don't need to know the deep math behind each.
Phew!
Understanding when to use which one is practical.
7. That is a lot of choices. How do you pick in a real-world scenario? What's the guidance?
Good question. It really depends on your data's characteristics and scale. For instance, SVD uses singular value decomposition. Koleski uses a direct matrix decomposition. Both are pretty good for smaller to medium-sized dense data sets where you don't have too many features.
Okay, SVD and Koleski for smaller, dense data. What about big data?
For large-scale data, especially if it's sparse, Sparseg conjugate gradient solver is often recommended.
Ah, like our text data example again.
Exactly. Then there's LS-Square, which is often noted as being very fast in practice. It's a dedicated, regularized least squares routine.
Faster is good.
Definitely. Then you have SAG and Saga. These are stochastic average gradient descent methods. Saga is a slightly more advanced version. These two are excellent choices when both your number of samples and your number of features are large.
Both large. Okay.
Yeah, because they're incremental solvers processing data in batches. But there's a catch. For SAG and Saga to converge quickly and reliably, your features really need to be on approximately the same scale.
Ah, so feature scaling becomes important if you use SAG or Saga.
Very important, yes. Without scaling, they might converge slowly or poorly. And finally, PalmBFGs is another popular and robust solver, a quasi-Newton method.
Wow, okay. Lots of options tailored to different situations. What if you're just starting out and not sure? Can scikit-learn help you choose?
It can. That's where Solver Auto comes in. This is actually the default setting, and it's pretty convenient.
Auto. I like the sound of that.
Yeah. The auto solver automatically tries to pick the best solver based on the type of data you feed. It's sparse or dense. How big is it? It aims to optimize for efficiency and robustness. It's a really good starting point.
Great default. Okay, one more parameter. Fit intercept. What's that about? When would you turn it off?
Fit intercept controls whether the model should estimate an intercept term, also known as a bias term. Basically, it allows the decision boundary to shift away from the origin. By default, it's true, which is usually what you want.
You know, true. When would it be false?
The main scenario where you'd set fit intercept false is if your data has already been centered. That means you've pre-processed it so that the mean of each feature is 0.
Ah, if you've already centered the data.
Right. If your data is centered, the optimal decision boundary is likely to pass through or very close to the origin anyway, so estimating an explicit intercept might be redundant or even slightly destabilizing. So if data is centered, set it to false. Otherwise, leave it as true.
Got it. Little optimization detail there. And for making predictions, once it's trained, it's just the standard predict method we discussed.
Exactly. Once your ridge classifier is fitted, you just call ridgeClassifier.predict xtest like any other classifier to get your class labels.
Simple.
And it's worth a quick mention, there's also a ridge classifier CV. The CV stands for cross-validation. It's a version that has built-in cross-validation to automatically find the best alpha value for you.
Oh, handy. Takes care of tuning alpha automatically.
Yep, simplifies that process quite a bit.
Okay, that's incredibly thorough on Ridge Classifier. Now, shifting gears again, let's talk about the perceptron. It sounds almost historical, like from the dawn of AI. What makes it still relevant and a practical choice in scikit-learn today?
You're absolutely right. The perceptron is one of the simplest and oldest classification algorithms, dating back to the late 1950s. But its simplicity is actually one of its biggest strengths, even now.
Simplicity as a strength. How so?
Well, it makes it incredibly suitable for large-scale learning. It's computationally very lightweight, meaning it can process data extremely quickly. It can handle massive data sets efficiently, especially if the underlying pattern is, or is close to being, linearly separable. And it's still a fundamental building block for understanding more complex neural networks.
Interesting. So speed and scale. And how is it implemented in scikit-learn? Does it also use that stochastic gradient descent thing like SGD classifier?
It does, and that's a key insight into scikit-learn's design. The perceptron classifier actually shares the same underlying implementation with SGD classifier.
Oh, really?
Yeah. In fact, you can create a perceptron just by using SGD classifier and setting its loss function to perceptron, the initial learning rate 8.0 to 1, learning rate to constant, and turning off the penalty.
None. So SGD classifier can be a perceptron.
Exactly. It highlights again how SGD classifier is that generic framework. The perceptron essentially uses SGD for its iterative training updates, adjusting its weights each time it misclassifies an example.
Okay, so it's a linear model trying to draw a line or hyperplane to separate classes. Can you quickly recap its core logic? How does it actually decide the class?
The core logic is really straightforward. It calculates a linear combination of its learned weights and the input features for a given sample. Think of it as a weighted sum.
Okay, weighted sum.
This sum is then passed through a very simple activation function, basically the sign function. If the sum is greater than or equal to 0, it assigns one class label, like +1. If the sum is less than 0, it assigns the other class label, like -1.
Simple thresholding, basically.
Pretty much. And it has a specific loss function it tries to minimize, often called the perceptron loss, max to WTXDXIY. Basically, it only incurs a loss and triggers a weight update if the prediction WTXI has the wrong sign compared to the true label YI. If the prediction is correct, the loss is 0 for that sample.
And does it always find a perfect separating line? Or can it get stuck?
Not always. That's a key characteristic. It's convergence behavior. If your data is linearly separable, meaning a perfect line or hydroplane does exist to separate the classes, the perceptron algorithm is guaranteed to find it and converge to 0 training loss in a finite number of steps.
Guaranteed if separable. What if it's not?
If the data is not linearly separable, the perceptron won't converge. It will essentially just oscillate, adjusting weights back and forth indefinitely, never quite settling on a solution that classifies everything correctly. It keeps making mistakes.
So that's a big limitation. If your data is complex, not linearly separable, perceptron might just keep bouncing around.
Exactly. It's an important limitation to remember. If your data has complex, nonlinear boundaries, a basic perceptron might not be the best choice on its own.
Good to know. How much can you customize a perceptron in scikit-learn? What are the key knobs to turn?
You actually have a decent amount of control, especially for such a simple model. You can add regularization using the penalty parameter, choosing between L1, L2, or ElasticNet to control complexity and fight overfitting.
Regularization. Okay. What else?
You can set the regularization strength with alpha, though its default is tiny, 0.0001, meaning very light regularization by default. For ElasticNet, there's L1 ratio to mix the penalties. Like ridge classifier, you can control fit intercept.
Intercept, got it.
Other important ones are maxiter, the maximum number of passes over the training data, epochs, defaulting to 1,000. There's toll for setting a stopping criterion based on improvement. Edo 0 is the initial learning rate, default is 1. And you also have options for early stopping.
Early stopping, to prevent overfitting.
Exactly. Parameters like early stopping, validation fraction, and night or no change let you monitor performance on a holdout validation set and stop training automatically if the performance stops improving, which saves time and helps prevent overfitting.
That's useful. And are there specific features that make it particularly good for those large-scale learning problems you mentioned, beyond just its speed?
Yes. 2 features really stand out for large-scale learning, especially when the data doesn't fit in memory. First is partial fit.
Partial fit. What does that do?
It allows for iterative training on mini batches of data. This is crucial for online learning where data streams in or when your data set is just too massive to load all at once. You can feed it chunks of data and update the model incrementally.
So you can train it piece by piece. Very cool for huge data. What's the second feature?
The second is warm start true. When you set warm start to true in the constructor, any new call to fit or partial fit will initialize the model using the weights it learned from the previous run instead of starting from scratch.
Oh, so it remembers what it learned before.
Exactly. This can speed up training significantly, especially if you're training over many epochs using partial fit. Or if you're continuously updating the model with new batches of data over time, the model doesn't forget its prior learning.
That warm start sounds incredibly useful for systems that need to learn continuously, like recommendation engines or maybe fraud detection models that see new data all the time. Okay, let's shift gears to another absolute fundamental. Logistic regression. Now this one, the name. It always trips people up, right? It sounds like regression, but it's definitely a classifier.
Absolutely. That name is a classic source of confusion for beginners because it uses a logistic function, which maps outputs to probabilities and optimizes using techniques similar to regression. It got stuck with the name. But yes, logistic regression is unequivocally a classification algorithm.
Good to get that straight. I hear it has other names too.
It does, which can add to the fun. Sometimes it's called a maximum entropy classifier or a maxent, or even a log linear classifier. but they all refer to the same powerful model that predicts the probability of class membership.
Probabilities, okay. So what's its core goal? What objective function is it trying to optimize?
Logistic regression aims to minimize an objective function that combines two parts, a regularization penalty and the cross-entropy loss. Specifically, it minimizes regularization penalty plus C cross-entropy loss.
Okay. Regularization plus cross-entropy loss scaled by C. What's that C parameter? Is it like alpha?
This is another potential. Gotcha. C here is the inverse of the regularization strength.
Yeah.
So unlike alpha in Ridge or perceptron, where a larger value meant stronger regularization.
Here's the opposite.
Exactly. A smaller value of C leads to stronger regularization because it's like 1 divided by a small number, making the effective penalty larger.
Yeah.
Conversely, a larger value of C results in weaker regularization.
Wow, okay. Inverse relationship. Smaller C, stronger regularization. Larger C, weaker regularization. That is definitely something to remember. It feels counterintuitive at first. Is that a common stumbling block?
Yeah. Oh, absolutely. It's one of those classic quirks you just have to drill into your head when working with scikit-learn's logistic regression or support vector machines, which also use C this way. It really highlights why you need to understand what the hyperparameter does, not just assume based on its name or common patterns elsewhere.
Definitely a key takeaway.
Yeah.
Smaller C, more regularization. Got it. Okay, what are its overall capabilities in scikit-learn? Can it handle more than just binary problems?
Oh, yes. It's highly versatile. It handles binary classification very naturally. That's its bread and butter. But for multi-class problems, it supports two main strategies.
Two strategies for multi-class.
Yep. It can do the one versus rest OVR strategy, where it trains a separate binary classifier for each class against all others. Or it can perform a direct multinomial logistic regression, sometimes called softmax regression, which trains a single model capable of outputting probabilities for all classes simultaneously.
Okay, OVR or multinomial, and regularization options.
It's flexible there, too. It supports L1, lasso, L2, ridge, and Alaskan added penalties, just like some of the others we've discussed.
Good. And training. Still the standard fit, XY.
Yes, the core training process is the same. You instantiate logistic regression, maybe set some parameters like C or the penalty, and then call model.fit xtrain, ytrain. Simple interface.
But the magic is often in the details, right? Like the solvers. Does it have different optimization algorithms too?
It does, and the choice of solver is actually quite crucial for logistic regression. Maybe even more so than for Ridge sometimes. It can significantly impact training speed, convergence, and even whether certain features, like penalties or multi-class strategies, are supported.
Okay, so choosing the right solver matters. What are the options here? Same as Ridge.
Not entirely the same. Logistic regression offers 5 main solvers: Newton CG, Pound BFGs, LibLinear, SAG, and Saga.
Newton CG, LBFGZs, LibLinear, SAG, Saga. Another list. Can you give us the practical guidance? When to use which?
Absolutely. Here's a rough guide. For smaller data sets, maybe tens of thousands of samples, LibLinear is often a good, robust choice. It tends to converge well and is quite efficient for that scale.
LibLinear for small. Got it.
For larger data sets, hundreds of thousands, millions, SAG and Saga are typically much faster because they're stochastic gradient methods, like SGD.
SAG and Saga again, like in Ridge. And the same scaling caveat applies.
Exactly the same caveat. They're very sensitive to feature scaling. If your features aren't on roughly the same scale, SAG and Saga might struggle to converge or give poor results. So, scale your data if you use them.
Scale for SAG Saga. Okay. What about the others? Newton CG and Pound BFGs.
Pound BFGs is actually the default solver in scikit-learn. It's a good general-purpose choice, often performs well, and is less sensitive to scaling than SAG Saga. Newton CG is another option, also fairly robust, sometimes good for high-dimensional data. Both Pound BFGs and Newton CG, along with LibLinear, are generally more robust if your data isn't perfectly scaled.
So LBFGs is the default, good all-rounder. LibLinear for small, SAG Saga for large, but scale. That helps narrow it down. Any other constraints maybe related to multiclass?
Yes, a very important one. If you want to use the multinomial loss strategy for multi-class problems, which often performs better than OVR as it models all classes jointly.
Right, the direct multi-class approach.
Then LibLinear cannot do it. LibLinear only supports the one versus rest OVR scheme for multi-class. To use multinomial loss, you must choose one of the other solvers: Newton CG, Pound BFGs, SAG, or Saga.
Okay. That's a critical compatibility issue. LibLinear only does OVR for multiclass. Need Pound BFGs, SAG, Saga, or Newton CG for multinomial. Good to know. What about the regularization penalty? Any compatibility issues there too?
Yes, another crucial point. Not all solvers support all penalties. This trips people up all the time.
Oh boy, okay, what's the deal here?
By default, logistic regression uses an L2 penalty, which is the most widely supported all solvers: LibLinear, Newton CG, Pound BFG, SAG, Saga can handle L2.
L2 is safe. What about L1 or elastic net?
If you want to use L1 penalty for feature selection, creating sparsity, or a elastic net, only LabLinear and Saga support them. The others, Newton TG, MBFG, SAG, only support L2 or no penalty none.
Wow. So if you want L1, you have to use LabLinear or Saga. If you use PoundBFGs, the default, you can only use L2. That's definitely a key detail for avoiding errors.
Absolutely. Trying to use, say, L1 penalty with the PoundBFG solver will just give you an error. You have to match the penalty to a compatible solver. Check the docs.
Will do. Okay, one more common challenge. Class imbalance. We touched on this before. How does logistic regression handle situations where one class is way rarer than others, like in fraud detection or medical diagnosis?
It handles this very elegantly using its class weight parameter. This is a really powerful feature.
Class weight, how does it work?
It allows you to assign different weights to different classes during training. By giving a higher weight to a minority class, you effectively tell the model, mistakes on this class are more costly. Pay more attention to getting this class right.
So you can increase the penalty for misclassifying rare but important examples.
Exactly. If you're detecting a rare disease, you might give the disease class a much higher weight. The model will then be heavily penalized for missing those positive cases, false negatives, even if it means making a few more false positives on the majority class. It forces the model to focus on the rare class.
That sounds incredibly useful for real-world problems where the cost of errors isn't symmetrical.
It really is. And this class weight parameter isn't unique to logistic regression. Many other scikit-learn classifiers, like SVMs and tree-based models, also offer it. It provides a consistent way to tackle imbalance across different algorithms.
Great. And finally, does logistic regression also have that handy CV variant for automatic tuning, like rich classifier CE?
Yes, it does. There's logistic regression CV. It bundles logistic regression with built-in cross-validation.
Nice. And what does it tune? The C parameter.
Exactly. It's fantastic for automatically finding the optimal value for C, that inverse regularization strength, and also L1 ratio if you're using elastic net. You give it a range of C values to try a CS parameter, specify a scoring metric, and it uses cross-validation to find the best one.
Streamlines the hyperparameter tuning process considerably.
Love it. Saves you writing those manual grid search loops.
Okay, that covers logistic regression really well. Now, let's circle back briefly to the generic SGD classifier. We mentioned its versatility early on. Given what we've learned about Ridge, perceptron, and logistic regression, how does SGD classifier stack up? When would you explicitly reach for it instead of one of the specific ones?
Right. SGD classifier, as we said, is that highly efficient approach for fitting linear classifiers, especially under convex loss functions. You'd explicitly choose it when you're dealing with really large-scale problems.
The truly massive ones.
Yeah, hundreds of thousands, millions of training examples or features. It's incremental, batch-wise training, partial fit, makes it ideal for data sets that just won't fit into memory, or for those online learning scenarios where data streams in continuously.
And its strength with sparse data.
That's the other key area. It absolutely excels with sparse data, making it the workhorse for tasks like text classification, MLP, where you have massive feature spaces, but most entries are zero. It handles that very efficiently.
Okay, so scale and sparsity are its big selling points. And it handles multi-class too.
Yes, it supports multi-class classification right out of the box using the one versus all OVA scheme. It just trains a separate binary classifier for each class behind the scenes.
So it's the go-to for massive scale, sparse data, or online learning. And you customize its behavior mainly through that loss parameter, right? Turning it into different models.
Exactly. The loss parameter is its magic wand. Set loss hinge, the default, and you get a linear support vector machine.
Okay.
Set loss log or log loss, you get logistic regression. Loss modified Huber gives a smoothed hinge loss, good for outliers, gives probability estimates. Loss perceptron trains the perceptron, as we discussed earlier.
Wow.
You can even use regression-style losses like squared error or Huber if you want to frame your classification that way. This flexibility is why it's such a powerful Swiss Army knife.
It really can mimic many of the specific classifiers. That's amazing flexibility. What are the potential downsides or things to watch out for when using it?
While it's powerful, it's not always plug and play. SGD classifier often has several hyperparameters that need careful tuning to get the best performance, things like the learning rate schedule, learning rate, the regularization strength, alpha, the number of iterations, maxiter. It can sometimes require a bit more experimentation to find the sweet spot compared to some specific solvers.
So potentially more tuning involved? Anything else?
Yes. Critically, it is highly sensitive to feature scaling. We mentioned this with SAG-Saga solvers, but it's generally true for SGD-based methods.
Scaling is vital for SGD classifier.
Absolutely vital for good performance and fast convergence. You really need to standardize or normalize your features so they're all on a similar scale. Example means 0, unit variance, or scaled to 0-1 range. If you don't, features with larger values can dominate the gradient updates, leading to slow convergence or a suboptimal model.
Okay, scale your data. Good practical tip. Any other best practices?
Shuffling your training data before each epoch is also generally recommended, especially if using partial fit. Since SGD processes data sequentially or in batches, shuffling helps prevent biases that might arise from the order of samples.
Shuffle the data. Got it. And how do you handle regularization and the number of training passes?
So regularization, it supports L1, L2, and elastic net penalties via the penalty parameter, just like logistic regression. Default is L2. The strength is controlled by alpha, default 0.0001. For elastic net, L1 ratio, default 0.15, mixes L1 and L2.
Okay, standard regularization options and epochs.
The number of passes over the training data, epochs, is set by Maxiter, defaulting to 1,000. You might adjust this based on convergence. Maybe you need more for complex data, or fewer if it converges quickly. Many of these parameters, like learning rate schedules, warm start, early stopping, are shared with its regression counterpart, SGD regressor, so there's good consistency there if you use both.
Fantastic. That's a really comprehensive look at the individual classifiers. We've seen how powerful scikit-learn is for binary and even multi-class problems. Now, let's move on to handling what you called multi-learning classification more formally. This area feels like the terminology can get a bit tricky. Can you help us nail down the distinctions between, say, multi-class, multi-label, and multi-class, multi-output?
Absolutely. This is definitely an area where clear terminology helps avoid confusion. And choosing the right approach depends on understanding these distinctions. Let's break them down.
Please do.
First, multi-class classification. This is probably the most common scenario people think of beyond binary. Here, each sample belongs to exactly one class, but there are more than 2 possible classes in total.
One label per item, but many possible options for that label.
Precisely. Think of our MNIST digit recognition example again. An image is either a 0, 1, or a 1 or a 2 up to 9. Can't be a 0 and a 1 at the same time, one exclusive label from a set of many. Or the iris dataset. A flower is setosa, versicolor, or virginica. One and only one.
Okay, multi-class equals one label, 2 options. Got it. What about when an item can belong to multiple categories simultaneously?
Right, that brings us to the next 2 categories, which both involve more than one label per sample. First, there's multi-label classification. Typically, this means each sample can be assigned 0, 1, or more labels from a set, and each individual label is usually treated as a binary decision. Present, absent, yes, no.
So multiple yes-no questions for each sample.
Kind of. Think about tagging a blog post. A single post might be tagged with technology, Python, and machine learning. Each tag is like a binary label. Does this post relate to technology? Yes, no. Does it relate to Python? Yes, no. An image might be labeled dog and cat if both are present.
Okay, multiple binary labels possible per sample. What's the third type?
The third type is multi-class, multi-output classification, sometimes called multitask classification. This is arguably the most complex. Here, each sample has multiple output labels, and each of those output labels can itself have more than 2 categories, i.e. each output is multi-class.
Whoa, okay. Multiple labels, and each label has multiple options. Can you give an example?
Sure. Imagine predicting properties of a product based on its description. Output 1 might be category, with options like electronics, clothing, home goods. Output 2 might be target audience, with options like adults, children, teens. Output 3 might be material, cotton, plastic, metal. A single product description would get a prediction for each of these outputs, and each output has its own set of mutually exclusive categories.
Okay, that clarifies it. Multi-class, one label, 2 options. Multi-label, multiple binary labels. Multi-class, multi-output, multiple multi-class labels. That's a helpful breakdown. And you use the umbrella term multi-learning problems for all of these?
Yes. For simplicity in discussion sometimes, multi-label and multi-class multi-output are often broadly grouped together as multi-label classification or multi-output classification because they both involve predicting multiple things per sample. But the overarching term that covers all 3 distinct types is multi-learning problems.
That really maps out the landscape nicely. Now, given these complexities, how do we actually represent these complex labels in scikit-learn? Especially when you have multiple possibilities or multiple labels per sample, you can't just use a simple list of numbers like 1, 0, 2, 1, can you?
You're right, a simple 1D array often isn't sufficient, particularly for multi-label or when using certain algorithms. A key tool here is the label binarizer from sclearn.preprocessing.
The little binarizer, what does it do?
It helps transform your label data, often a single vector of categories, into a binary matrix format. This format is often called a one-hot encoding or an indicator matrix.
One hot encoding, so it creates columns for each class.
Exactly. If you have, say, n samples and k unique classes in your original label vector, label binarizer converts it into a binary matrix of shape, n samples and classes. Each column corresponds to a class. For a given sample, row, a 1 in a column means that sample belongs to that class, and a 0 means it doesn't.
Can you give us that MNIST example again? How would it binarize the digit 5?
Sure. If you have an image labeled with the integer 5, label binarizer, when fit on all digits 0, 9, would transform that single label 5 into a 1 by 10 vector, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. Only the sixth position, index 5 representing the digit 5, is 1, all others are 0. This binary indicator matrix format is what many multi-learning algorithms or strategies like one-virus rest expect as their Y input.
That's super clear. Turns a category into a yes-no for each possible category. What if you're just handed a data set and you're not even sure what kind of labels you're dealing with? Binary, multi-class, something else. Is there a quick way to check programmatically?
Absolutely. And this is a really useful utility for data validation before you start modeling. Type of target from sclearn.utils.multiclass.
Type of target.
Okay.
You just pass your label data, your IG vector or matrix, to this function, and it will analyze it and return a string telling you what it thinks it is. It can identify binary, multi-class, multi-label indicator, our planarized format, multi-class multi-output, continuous multi-output, or unknown.
That sounds incredibly handy for just sanity checking your data format before you dive in.
It's a lifesaver. It helps you catch potential issues or mismatches between your data format and the algorithm you're planning to use right at the start. Saves a lot of debugging headaches later.
Definitely adding that to my checklist.
Yeah.
Okay, so we know the different multi-learning types and how to represent the labels. Now, let's talk strategies. Specifically for multi-class classification first, do you always need a special meta-estimator or strategy, or do some classifiers just handle it naturally?
It's a mix, and knowing the difference is important. Many common scikit-learn classifiers actually have built-in support for multi-class classification.
Oh, really? Which ones? Well, logistic regression, if you set multi-class multinomial, or even the default multi-class auto, which often chooses multinomial or OVR intelligently. Ridge classifier, which uses OVR internally. SGD classifier uses OVR, and Perceptron also uses OVR. For these, you often don't need an extra strategy wrapper. You just pass them your multi-class Y vector, like 0, 2, 1, 1, 0, and they know how to handle it internally.
So for those popular ones, multi-class is often just built in. When would you explicitly use one of those multi-class meta-estimators then, like the ones in sclearn.multiclass?
You typically use a meta-estimator in two main situations. First, if the base classifier you want to use doesn't have built-in multi-class support, maybe it's strictly a binary classifier, the meta-estimator wraps around it, allowing you to apply it to a multi-class problem.
Okay, extending binary classifiers. What's the second reason?
Second, you might use a meta-estimator even with a multi-class capable base classifier, if you want to explicitly control or experiment with a specific multi-class strategy, like 1v rest or 1v1, perhaps for comparison, or because you believe a particular strategy might perform better for your specific data or base estimator.
I see. So for forcing a specific strategy or enabling multi-class for binary-only estimators, let's look at the main strategies. First, 1v rest, OVR, sometimes called 1v all, OVA. How does that work conceptually?
1v rest is probably the most common and often the most computationally efficient strategy. The idea is simple. It fits one binary classifier per class.
One per class, okay.
For each classifier, it's trained to distinguish that specific class, let's call it class C, from all the other classes combined, which are treated as a single not C group.
So for MS-Digits 0, 9, it would train 10 separate classifiers.
Exactly. It would train 0 versus not 0, 1 versus not 1, versus not 2, all the way up to 9 versus not 9. 10 independent binary classifiers.
And how does it make a prediction for a new image then?
When you give it a new image, all 10 classifiers make a prediction and usually output a confidence score using decision function. The class whose corresponding binary classifier gives the highest confidence score is chosen as the final prediction for the image.
Okay, simple voting based on confidence. That sounds pretty efficient, only K classifiers for K classes.
It is indeed quite computationally efficient, especially if you have many classes. It scales well. The resulting model can also be reasonably interpretable, as you can examine each individual binary classifier. The 1V's rest classifier is the meta-estimator for this in scikit-learn. And interestingly, it can also handle multi-label classification if you feed it high labels in that binarized indicator matrix format.
Okay, OVR is efficient, interpretable. What about the other main strategy, 1V's is 1, OVO? How does that differ?
1V's 1 takes a completely different tack. Instead of one use all, it fits one binary classifier for every possible pair of classes.
Every pair. So for 3 classes, A, B, C, it would do.
It would train A vs B, A vs C, and B vs C, 3 classifiers in total. Each classifier is only trained on the data points belonging to the 2 classes in its pair, and its job is just to distinguish between those 2.
That sounds like it could generate a lot more classifiers than OVR, especially if you have many classes, like for MNIST with 10 digits.
You're absolutely right. It can scale up quickly in terms of the number of classifiers. The formula is K, K1, 2. So for 10 MNIST digits, that's 10, 9, 2, keyword 45 classifiers, much more than the 10 classifiers needed for OVR.
45 classifiers. Wow, how does prediction work then? Do all 45 vote?
Pretty much. When a new sample comes in, each of the 45 binary classifiers predicts which of its 2 classes the sample belongs to. The class that receives the most votes across all these pairwise classifiers is declared the winner, the final prediction. Ties are usually broken based on aggregate confidence scores.
Okay, so why would you ever choose OVO over OVR, especially since it trains so many more models? It seems less efficient at first glance.
That's the key trade-off. OVO can actually be advantageous when the base classifier you're using doesn't scale well with the number of samples.
Ah, if the underlying algorithm itself is slow on large datasets.
Exactly. Think about algorithms like kernel SVMs, which can become computationally expensive as the dataset size grows. In OVO, each binary classifier is trained only on the subset of data belonging to its pair of classes. So each classifier trains on a potentially much smaller dataset than the full dataset used by each OVR classifier.
I see. So even though you train more classifiers, each individual training task might be much faster if the base algorithm struggles with scale.
Precisely. It breaks the big problem down into many smaller, potentially faster to solve subproblems. The 1V's own classifier is the meta-estimator for this strategy. So the summary is, OVR is generally more efficient in terms of the number of models, K, while OVO, KK12 models can be better if your base classifier is sensitive to the number of training samples.
That's a really clear explanation of the trade-off. It depends on the base algorithm's scaling properties. Okay, now let's quickly cover strategies for the truly multi-output cases. Multi-label and multi-class multi-output, where one sample can genuinely have multiple independent or related labels.
Right. For these scenarios, scikit-learn offers 2 main meta-estimators, multi-output classifier and classifier chain.
Okay, multi-output classifier first. What's its approach?
Multi-output classifier adopts a very straightforward strategy. It fits one independent classifier per target variable.
One per target. So if you're predicting, say, 5 different binary labels for an item, it trains 5 separate binary classifiers.
Exactly. If you have M target variables, which could be binary labels in multi-label, or multi-class outputs and multi-class multi-output, you train a completely independent classifiers. Each classifier learns to predict its specific target based only on the input features X.
So it assumes the targets are independent. It doesn't try to model relationships between them.
Correct. It treats each output prediction task in complete isolation. The benefit is simplicity and parallelism. You can train each classifier independently, maybe even in parallel. It's great when you believe the targets are mostly independent, or if you just want the simplest approach.
Okay, multi-output classifier for independent targets. What about classifier chain? The name suggests dependencies.
It does, and that's its key idea and potential advantage. Classifier chain is specifically designed for multi-label problems, multiple binary outputs. It arranges the binary classifiers, one for each label, into a chain.
A chain? How does that work?
The first classifier in the chain is trained on the input features X to predict the first label. Then the second classifier is trained using both the original features X and the prediction made by the first classifier to predict the second label. The third classifier uses X plus the predictions from the first 2 classifiers, and so on.
Whoa, so the prediction for one label becomes an input feature for predicting the next label down the chain.
Precisely. This allows the classifier chain to potentially exploit correlations between the target labels. If knowing that an image contains a dog makes it more likely to also contain fur, this chained approach can capture that dependency, potentially leading to better overall predictions if such correlations exist.
That's clever, but doesn't the order of the classifiers in the chain matter then?
Absolutely. The order can significantly impact performance. Finding the optimal chain order can sometimes be a challenge, often requiring experimentation with different random orders or using domain knowledge to define a sensible sequence. So the comparison is multi-output classifier for assumed independent targets, classifier chain for potentially exploiting correlations between binary labels, but with the caveat that order matters.
Fascinating strategies for complex outputs. Okay, we've covered training, algorithms, multi-learning. Now the crucial step, evaluating and tuning your classifiers. Because, as you said, training is only half the battle, right? Knowing how well it actually works and how to make it better is vital.
You're spot on. It's the moment of truth for your model. And while many general cross-validation and tuning methods like grid search CV or randomized search CV apply here just like in regression, classification has some specific wrinkles we need to address, especially around evaluation metrics and handling data imbalance during validation.
Right, class imbalance again. We know it can mess up simple accuracy. How does it specifically impact cross-validation if you're not careful?
It can seriously skew the results. Imagine that rare disease case again, 99% healthy, 1% disease. If you do a standard K-fold cross-validation, just randomly splitting the data into, say, 10 folds.
You might get some folds with 0 disease cases.
Exactly. By pure chance, some training folds might have no examples of the disease, so the model trained on that fold literally never sees the minority class. Or a test fold might have no examples, so you don't even evaluate performance on it in that split. This leads to unreliable, often overly optimistic performance estimates because the validation isn't representative.
So you need to ensure each fold mirrors the overall class distribution. How do you do that?
That's where stratified cross-validation comes in. Scikit-learn provides stratified versions of its cross-validation iterators in sklearn.model selection.
Stratified versions? Like what?
Key examples are stratified K-fold, repeated stratified K-fold, and stratified shuffle split. Stratified K-fold is like regular K-fold, but it ensures that the percentage of samples for each class is preserved in each fold.
Ah, so every fold looks like a mini version of the whole data set in terms of class proportions.
Precisely. Repeated stratified K-fold just repeats this process multiple times with different random shuffles for more robust estimates. Stratified shuffle split creates random Traintis splits that also preserve proportions, though its folds might overlap across iterations, unlike K-fold. Using these stratified iterators is crucial for reliable evaluation, especially with imbalanced data.
That's a critical point. Always use stratified CV for classification if possible. Can you show how this plugs into something like logistic regression CV?
Sure, logistic regression CV is designed for this. It has a CV parameter where you can explicitly pass a stratified cross-validation iterator object, like stratified K-fold in splits 5. It also has a scoring parameter where you define the metric you want optimized during the search for the best C value. You might choose accuracy, or maybe F1 macro or ROCAC if accuracy isn't suitable. And its CS parameter lets you specify the range of C values to test. It bundles stratified CV, parameter searching, and scoring all together.
Very convenient. Now, when doing this kind of cross-validated hyperparameter search, there's often a refit parameter. What does that control?
Right, refit is important. It's typically found in tools like grid search CV, randomized search CV, and also in logistic regression CV. It determines what happens after the cross-validation has identified the best set of hyperparameters.
Okay, so what is refit true? That's usually the default, right?
Yes, refit true is the default and most common usage. When it's true, the process first finds the hyperparameters that gave the best average score across all the CV folds. Then, and this is the key part, it performs a final refit of the model using those best parameters, but this time training on the entire data set, all the data used in the CV.
Oh, so it uses CV to find the best settings, then trains one final model on all the data using those settings.
Exactly. This gives you a single, final, production-ready model that has hopefully benefited from the tuning process and is trained on the maximum amount of available data. That's usually what you want to deploy.
Makes sense. What if you set refit false? When would that be useful?
If you set refit false, the cross-validation still runs, finds the best parameters, and calculates the scores. However, it doesn't do that final retraining step on the whole data set. Instead, it might return information about the best parameters found, the corresponding scores, or perhaps the best model from one of the individual folds.
Why would you do that?
You might do this if you only want to know what the best parameters are. perhaps for reporting or analysis, without immediately needing the final trained model. Or maybe you plan to do some custom ensembling or manual retraining later. It gives you the results of the search without the final fitted object.
Okay, clear distinction. Refit true gives the final model. Refit false gives the results of the search. Now, let's dive into the evaluation metrics themselves. We know simple accuracy score, can be misleading. What are the key alternatives and why are they so important?
This is where we get into the real substance of model evaluation. Accuracy is just the tip of the iceberg, its biggest flaw, as we saw with the dummy classifier example.
A 90% accurate but useless zero detector.
Exactly. It failed because the data set was imbalanced, 90%, not zero. Accuracy looked great, but it didn't reflect the model's ability to find the rare CROI class. So for imbalanced data, accuracy is often a poor metric.
So what's a better alternative for imbalance?
A much better choice is often balanced accuracy score. This metric calculates the recall, or true positive rate, for each class individually, and then averages those per-class recalls.
Ah, average recall across classes.
Yes, this gives equal weight to each class, regardless of its size. So even if the minority class recall is very low, it will pull down the balanced accuracy score, giving you a much more honest picture of performance across all classes.
That sounds much fairer for imbalanced problems. Any others?
We could briefly mention top accuracy score. This is useful in scenarios like recommendation systems, where you don't necessarily need the single top prediction to be correct, but you care if the true item is among the top, say, top 5 suggestions.
Okay. But for typical classification, beyond balanced accuracy, the real deep dive starts with the confusion matrix, right? Feels like the ground truth map.
Absolutely. The confusion matrix is fundamental. It's a table that neatly summarizes how your classifier performed by comparing the actual class labels to the predicted class labels.
How is it structured?
Typically, rows represent the true classes, and columns represent the predicted classes, or vice versa. Check the documentation. An entry at row I, column J, tells you how many samples that actually belong to class I were predicted by the model to be in class J.
So the diagonal entries IJ are the correct predictions.
Exactly. The diagonal shows your true positives for each class and true negatives implicitly. Everything off the diagonal represents errors, misclassifications. These are your false positives and false negatives.
And seeing where those off-diagonal numbers pile up tells you where the model gets confused.
Precisely. In our MS multi-class example,
Yeah.
if you saw a large number in the row for true 8 and the column for predicted 3, it immediately tells you the model frequently confuses 8s with 3s. This is invaluable diagnostic information. Scikit-learn also has a confusion matrix display helper to plot it visually, which makes these patterns even easier to spot.
Okay, the confusion matrix gives the raw counts of correct and incorrect predictions by class. That naturally leads into precision, recall, and F1 score, which are calculated from those counts, right? Let's define them clearly.
Yes, these are key metrics derived directly from the confusion matrix values. True positives TP, true negatives TN, false positives FP, false negatives FN.
This measures, out of all the samples your model predicted as positive, what proportion were actually positive. The formula is TP plus FP, it answers. When my model predicts positive, how often is it correct? High precision means low false positive rate.
Okay, precision is about the accuracy of positive predictions. What about recall?
Recall, also called sensitivity or true positive rate. This measures, out of all the samples that were actually positive, what proportion did your model correctly identify as positive? The formula is TP plus FN. It answers. Of all the actual positive cases, how many did my model find? High recall means low false negative rate.
Got it. Precision, correctness of positive predictions. Recall, completeness of finding actual positives. And F1 score.
F1 score. This is the harmonic mean of precision and recall. Formula 2. Precision recall. Precision plus recall. It provides a single score that balances both precision and recall. It's particularly useful when the cost of false positives and false negatives are similar, or when you need a single metric that accounts for both aspects. It tends to be high only when both precision and recall are high.
Harmonic mean. That penalizes extreme values more than a simple average, right?
Exactly. If either precision or recall is very low, the F1 score will also be low. It forces a balance.
Now, we often hear about this trade-off between precision and recall. What does that mean in practice, and why is it so critical?
It's a fundamental tension in most classifiers. Often, if you adjust your model or its decision threshold to increase precision, i.e. reduce false positives, you will inadvertently decrease recall, i.e. increase false negatives, and vice versa.
Why is that?
Think about setting the confidence threshold. If you want really high precision, very few false positives, you might set a very high threshold, only classify as positive if the model is extremely confident. But doing so means you'll likely miss some true positives that had slightly lower confidence scores, thus lowering recall.
And the opposite, if you want high recall.
If you want high recall, catch almost all true positives, you might lower the threshold. This will find more true positives, but you'll also likely classify more negative samples incorrectly as positive, increasing false positives and thus lowering precision.
So you usually can't maximize both simultaneously. You have to choose which is more important for your problem.
Precisely. The choice depends entirely on the application's context and the relative costs of FP versus FN errors. For spam filtering, precision is key. You really don't want to misclassify important emails as spam high cost of FP. For screening for a serious disease, recall is often paramount. You want to find as many cases as possible, even if it leads to more false alarms needing follow-up high cost of FN. Understanding this trade-off is crucial for building responsible and effective models.
That makes perfect sense. That's about the consequences of different types of errors. And to help visualize this trade-off, we have the precision recall curve.
Exactly. The precision recall PR curve plots precision y-axis against recall x-axis for various decision thresholds. As you move along the curve, implicitly changing the threshold, you see how precision drops as recall increases and vice versa. The precision recall curve function in scikit-learn gives you the points to plot this. It helps you choose a threshold that achieves a desirable balance for your specific needs.
Okay, PR curve shows the direct trade-off. What about the other common curve, the ROC-AUC curve, receiver operating characteristic?
Right, the ROC curve is another way to visualize classifier performance across thresholds. It plots the true positive rate, TPR, which is just recall, on the y-axis against the false positive rate, FPR, on the x-axis. FPR is the proportion of actual negative samples that were incorrectly classified as positive, FP plus TN.
TPR versus FPR. What does a good ROC curve look like?
An ideal ROC curve would hug the top left corner. High TPR, high recall, and low FPR, few false alarms. A random classifier would produce a diagonal line from 0, 0 to 11, 1. The area under this curve, AUC, the ROC-AUC score, provides a single number summarizing the classifier's ability to distinguish between positive and negative classes across all thresholds. An AUC of 1.0 is perfect, 0.5 is random guessing. Higher AUC generally means better overall discrimination ability. The raw curve function helps generate this.
So PR curve is good when you care deeply about the positive class and precision recall balance, especially with imbalance. RC-AUC gives a more general view of separability across all thresholds.
Got it. Lots of metrics. Is there a single function that wraps up the main ones for a quick summary? Yes, and it's incredibly useful classification report. You just feed it your true labels and predicted labels, and it prints out a nice text report.
What's in the report?
It shows the precision, recall, and F1 score calculated for each class individually. It also includes the support, number of true instances for each class, the overall accuracy, and often macro and weighted averages of precision, recall, and F1. It's usually the first thing you'll look at after running Predict to get a comprehensive overview of performance across all classes.
Classification report definitely sounds like a go-to summary tool.
Okay.
That's a great rundown of the binary or per-class metrics.
Yeah.
How do we aggregate these for multi-class and multi-label problems overall? You mentioned averaging.
Yes, the core idea is to calculate the metric like precision or F1 for each class as if it were a binary problem, class versus rest, and then average these per class scores. Scikit-learn's metric functions typically have an average parameter that controls how this averaging is done.
Okay, what are the common averaging strategies?
The main ones you'll encounter are macro. Calculates the metric for each class independently and then takes the unweighted average. Every class contributes equally, regardless of its size. Good if you care about performance on all classes equally, including rare ones.
Macro, unweighted average. Fair to all classes.
Weighted. Also calculates the metric for each class, but the average is weighted by the number of true instances for each class, the support. This gives more importance to the performance on larger classes. Useful if you want the overall metric to reflect performance on the predominant classes or account for imbalance.
Weighted reflects overall distribution.
Micro. Calculates the metric globally by counting the total true positives, false negatives, and false positives across all classes combined. It gives equal weight to each individual sample's classification decision. For metrics like precision, recall, F1, microaveraging often yields the same result as overall accuracy in multi-class settings.
Micro global calculation based on total TPFPFN treats every sample equally.
Samples. This calculates the metric for each sample individually. For example, for multi-label, how many labels were correct for that sample, and then averages over all samples, primarily used for multi-label classification.
Samples average per sample score. Good for multi-label.
None. If you set average, none. It doesn't average at all. It just returns an array containing the metric calculated for each class separately. This is great for seeing the detailed per-class performance.
Wow, that average parameter is incredibly powerful for tailoring the evaluation to exactly what you need to measure. Macro for fairness, weighted for imbalance-aware average, micro for overall sample performance, samples for multi-label, none for details.
Yeah.
Fantastic. Okay, we've covered so much ground. Let's bring it all together in this final section. Practical applications and advanced customization. Let's revisit that MNEST digit classification demo you mentioned. What key learnings came out of that which illustrate these concepts?
The MNEST demo is such a great pedagogical example because it lets us see many of these ideas in action. Let's start with the binary case again, the zero detector using a perceptron.
Right, just detecting zero versus not zero. What were the steps?
First, data prep. MLP is 70,000 images, 28 by 28 pixels, so 784 features. Crucially, we used min-max scaler to scale those pixel values from the original 0255 range down to 01.
Scaling. Vital for perceptron SGD, as we discussed.
Absolutely vital. Then the baseline. We used that dummy classifier with strategy most frequent. It predicted not zero every time.
And got 90% accuracy because most digits aren't zero.
Exactly. Highlighting perfectly why accuracy is insufficient here. It told us nothing about whether we could actually find the zeros. It underscored the need for precision, recall, F1, and the confusion matrix.
So how did the actual perceptron do?
The perceptron, once trained, performed remarkably well. Accuracy was high, like 0.99 train, 0.98 test. But more importantly, the confusion matrix showed very few false negatives, missed zeros, and few false positives. Non-nit is called zero. Precision and recall for the zero class were both high, confirming it was actually doing the job we intended, unlike the dummy baseline.
Great. A real demonstration of needing better metrics.
Yeah.
What about the multi-class case, identifying all 10 digits with the perceptron? How did data prep change?
For multi-class, the key change was handling the phi labels. Instead of just 0 or not 0, we had labels 0 through 9. To feed this into the perceptron, which uses one versus rest internally, we used label binarizer.
The binarizer again, to turn 5 fillet into 0000010010010.
Exactly. It converted our 60,000 training labels, single digits, into a 60,000 by 10 binary matrix. This is the format the perceptron needed to learn its 10 sets of weights, one set for distinguishing each digit from the rest.
So it learned 10 internal binary classifiers. What were the results?
The overall accuracy was pretty good, around 0.90 on the test set, but the real insights came from the multi-class confusion matrix.
What did that show?
It clearly highlighted the specific errors the model was making. For instance, you could see a non-trivial number of actual 8s being misclassified as 3s or 5s, and 9s were sometimes confused with 4s. 2s and 3s also had some confusion. Seeing these specific pairwise confusions is gold dust for understanding model weaknesses.
Absolutely. Pinpoints exactly where it struggles. Now, thinking about the overall workflow, you mentioned pipelines earlier. How do they help in this kind of process?
Pipelines, slurn.pipeline.pipeline, are fantastic for organizing and ensuring correctness. In the MNIST example, you'd create a pipeline containing both the min-max scaler and the perceptron estimator.
So scaling and classifying bundled together.
Yes. This does two crucial things. One, it simplifies your code you just call fit and predict on the single pipeline object. Two, and more importantly, it prevents data leakage during cross-validation.
How does it prevent leakage?
When you use a pipeline within, say, grid search CV or cross-vol score, the scaling step, like min-max scaler, is automatically fitted only on the training portion of each fold, and then used to transform both the training and validation test portions of that fold. It ensures no information from the validation test set leaks into the scaler's fitting process, giving you more reliable performance estimates. Pipelines enforce good practice.
That's a huge benefit for robust evaluation. And you also mentioned hyperparameter tuning for the perceptron, finding the best eta.
Right. We use Gray Search CV to tune the initial learning rate, ETOO. Grid Search CV systematically tried several values, like 0.5, 0.25, 0.125, etc.
And it found the best one.
Yes, it found that ETI 0.125 yielded the best performance, e.g. lowest loss or highest accuracy, during crocked validation. This just demonstrates that even for simple models, tuning key hyperparameters can provide noticeable improvements over default values. It's worth the effort.
And you could even approximate learning curves using partial fit.
Yeah, that was a neat trick. Since Perceptron supports partial fit, You can call it repeatedly on small batches and track the performance, for example, loss or accuracy on a held-out set, after each batch. Plotting this performance over the number of batches iterations gives you an approximate learning curve, showing how the model improves over time and helping diagnose convergence or overfitting issues.
Very cool. Finally, let's talk about that model introspection again, looking inside the model. Visualizing weights and activation maps, how did that provide insight in the MNIST case?
This is where it gets really fascinating. For linear models like our Perceptron Zero detector, it learned a weight vector with 784 weights, one per pixel. If you reshape that vector back into a 28 by 28 grid and visualize it.
You can see what the model learned looks like.
Exactly. You often see positive weights concentrated in the areas where a zero typically has ink, and negative weights in areas where other digits might have ink but a zero doesn't, or around the edges. It's like seeing the template the model is looking for.
That's amazing. You're seeing its internal representation.
Yeah.
And activation maps.
Activation maps take it a step further for a specific input image. You multiply the input image's pixel values by the learned weights, pixel by pixel, and visualize the result. If you feed it an image of a zero, the activation map will likely show strong positive activations where the zero shape aligns with the positive weights, leading to a large positive sum and a narrow prediction.
And if you feed it a 5.
The activation map might show strong negative activations where the 5-foot hits negative weights in the zero template, leading to a negative sum and a not zero prediction. It visually shows why the model made the decision it did for that specific input. It's incredibly helpful for debugging misclassifications. You can see which parts of the image led the model astray.
That's truly like having X-ray vision into the model's decision process. Invaluable for understanding and trust.
It really helps demystify the black box to some extent, especially for these linear models.
Wow, what a comprehensive journey we've taken today. We started with the core scikit-learn APIs, distinguishing generic SGD classifier from specific ones like ridge classifier, perceptron, logistic regression. We dove deep into how each of those works, their parameters, their solvers, their strengths. Then we navigated the complexities of multi-learning, multi-class, multi-label, multi-output, and the strategies like OVR, OVO, multi-output classifier, classifier chain.
And then the crucial part, evaluation and tuning. We covered why accuracy isn't enough, the importance of stratified cross-validation, balanced accuracy, confusion matrices, precision, recall, F1, PR curves, ROC curves, and how to average metrics for multi-learning problems.
Exactly. And finally, we tied it all together, seeing it in action with the MNIST demo, highlighting scaling, baselines, pipelines, hyperparameter tuning, and even that amazing model introspection with weight visualization and activation maps.
Indeed. Hopefully you listening now have a much more solid foundational understanding of how to implement, customize, and critically assess machine learning classifiers using scikit-learn. It's not just theory, it's a really powerful toolkit for turning data into actual insights and informed decisions.
Absolutely. So as you go forward, here's something to think about. We talked a lot about trade-offs, like precision versus recall. And we talked about data characteristics like class imbalance. Given these nuances, how might really understanding them change how you approach real-world problems? How do you move beyond just chasing the highest accuracy number?
A critical question.
And perhaps more deeply, what ethical implications might arise when a model, by design or by tuning, prioritizes a one metric over another, say, recall over precision in healthcare screening, or precision over recall in loan applications? How do you, as a builder or user of these systems, navigate those choices responsibly? Something powerful to mull over as you continue your own deep dives.
A truly vital consideration. Those metric choices have real-world consequences.
Couldn't agree more. Thank you so much for joining us on this deep dive into scikit-learn classification. We'll catch you next time.